Okay, 8.4, choosing a sample size. What this is you can determine how big of a sample you need to grab in order to get certain desired results. And that kind of depends on your confidence level and the maximum margin of error that you're okay with. Then we can find a way to calculate the minimum sample size in which you would need to meet these goals. So what should my sample size be? It kind of depends on what confidence interval you want, level. So do you want to be 90% confident, 95% confident, 99% confident? What is the maximum major of error, E, that you want? And again, we're going to assume that these follow some sort of normal type of distribution. So basically, we're going to take this error formula that we got from before, and we're going to manipulate it a little bit. We're going to take that, and with a little of algebra, we'll get that solved for n. So now I can use a critical value. I need to know the standard deviation, in fact, the population standard deviation, and that error that I'm okay with to figure out what that sample size is. There's only one formula for, standard deviation, and that's with population standard deviation. We either need to know that it comes from a normal curve, or if n is big enough, it's bigger than 30, we'll take and use the sample standard deviation in its place. Okay, but I want to stress there's only one formula to figure out the sample size for a mean. Okay, so don't think there's one with an S involved and don't create your own either. And this formula, again, is in the formula sheet. Make sure that you always round your n value up to the next integer, even if the rounding doesn't work out that way. So if you end up at the 0.1, round it up to the next whole number to be okay. So my scenario is I've got a golf ball manufacturer who wants to estimate the maximum distance of its new prototype can fly under ideal conditions, a preliminary mechanical study of 36 shots. Okay, 36 is bigger than 30, so we're going to end up using this S as a good estimate for our population standard deviation. From those 33 shots, they got a sample standard deviation of 11 yards. How many test shots should we complete to get a maximum distance within 2 yards? So their average they want to claim is going to be within 2 yards, whether it's plus 2 yards or minus 2 yards, at a 95% confidence level. So look up the z-score for 95% confident, and that's what you're going to use for VC. Yeah, so I believe for 95%, that's 1.96. So again, there's only one formula that you're going to use here for the sample size for estimating mean, and that's n equals ZC, standard deviation, divided by your error squared. So I'm going to go ahead manipulate those numbers a little bit. My ZC 1.96, the standard deviation of 11, over to my desired error of 2, square that number. So 1.96 times 11, okay, divided by 2, square that, and I get about 116.2. But I'm going to round that up to 117 shots. Okay, now how many more would that be? Well, our preliminary study was 36, so really they could get their data after the 36 and go 117 minus those 36. They're going to need an additional 81 swings, okay, or hits of that golf ball. Sample size for p hat, again, p hat is your r over n. Here's what it started off for your maximum error. So with a little bit of algebra, it solves into that. They use the 1 minus p, but this is really p times q. Okay, your ZC is your critical score. We're still using the normal curve. You got your error that you're okay with, and then you've got that squared. When there's no preliminary p given, so you've got no p hat to go off of, you're going to use the following formula. So really the 1/4 comes from the fact that they're going to assume that p has a 50-50 shot, so 1/2 times 1/2. Again, that's only when you don't have a preliminary probability given to you. So here a bottle manufacturer wants to know the proportion of 12-ounce bottles are defective. From last month's study, approximately 3.3% of the bottles are defective. Okay, so our probability, and I'm going to take and convert that into a decimal, of a bottle being defective is 0.033 or 3.3%. How many bottles need to be sampled to pin down a true proportion of defectives to within an error of 0.9, so 0.009? Be careful to move that over 2 spots. We're still going to be 95% confident, so the same critical value of 9.6 or z-score. So for my p-hat, I'm going to take p, which is this proportion given to me, 1 minus that. So 0.97 for failure. And now my critical value of 1.96 divided by the error of 0.009. Okay, and just to double check, yep, I think I need to square that as well. Okay, so I always like to work with the fraction first, 1.96 divided by 0.09. Square that answer, and then I'm going to multiply by 0.97, and then the other 0.033. And I get n is equal to, here we go, rounding it up, 18.1, so 1,519 bottles. So I guess I got this from the last one of shots. But they need to test 1,519 water bottles to get the air to be within 3.3% defective and be 95% confident of that answer. Okay, here's your assignment, page 441, 1 through 7, 9, 14, and 16. I would suggest going through and doing quite a few of these. This assignment is kind of different from the others. So it's kind of like the different way of reading the results. So we'll practice this a little bit more in class, and let me know if you got any questions.